So we had left off last time talking about relative motion, particularly relative motion in terms of velocity, and we got to use that shortcut tool of the instantaneous center, which made that a lot easier than going through the vector expression, and we'll need to use that again in the future. But we're going to have to spend a lot more time with vectors as we look at acceleration, because there is no such thing as instantaneous center of zero acceleration. Your normal acceleration kind of throws that out the window. So if we take that expression for the velocity, the relative velocity, and we differentiate it with respect to time, we come up with the acceleration equation. For instance, that the acceleration of A is equal to the acceleration of B plus the acceleration of A with respect to B. So if I were to look at a situation here where I have this body that's rotating about B, and you could think of point B as fixed, that would make life easier. Eventually we will think about B accelerating in and of itself. But if this body is rotating with some angular velocity and angular acceleration, we could say that the acceleration of A with respect to B takes on two different pieces. It could have the piece in the tangential direction, which is r times alpha, where r would be this position vector that goes from B to A. Or it could have a piece in the normal direction that would be v squared over rho. We could replace that rho with r, or we could see it as r omega squared is probably more common. Certainly if you resolve those two components vectorially, you would get the acceleration of A with respect to B. Okay, so if I take this equation up here and I expand this over here, I could look at, say that in this particular case, that the acceleration of A is equal to the acceleration of B plus the acceleration of A with respect to B, and then I'll break up those. I'll say the acceleration of A with respect to B in the normal direction and A with respect to B in the tangential direction. And we could show what we get for the normal direction. That would be omega crossed with R. I think I've done that about twice in all these years. That's way too much work. Omega crossed with V, remember omega crossed with R is V. You could do that. But really the nice one here is minus omega squared R, or minus omega squared R. That's just a coefficient, and then you have the vector r, because the normal acceleration is really pointing in the opposite direction of r, isn't it? The acceleration in the tangential direction then is alpha crossed with r. So this looks like this is starting to get out of control, but it hasn't even begun yet, because the acceleration of b, if we're not moving in a straight line, if b is having circular motion, could b have a normal and tangential component? Absolutely. Okay. So a lot of times people think that these problems are hard. I wouldn't say that they're hard. They can be long, they can be tedious, they can be fraught with spots to make mistakes, but they're usually not hard. It doesn't take a lot of creativity. You always start with the same equation, and you start to expand it out, and then you put all of the pieces in there. When I was studying for my professional test for the mechanical one, I took a review class, and the fellow was nice enough fellow that did the review on dynamics, but he recommended we don't try problems like this. Okay, and you know that's his opinion and whatnot. I didn't follow it. I did problems like that because they're really not very creative. You start out with the same equation, you fill in the pieces. It doesn't take very long. It doesn't take a lot of thinking. So anyway, for what that's worth. Well, let's move into a problem of our own then. So let's say that we have this problem. We've got some sort of a disk here, and it has a 0.3 meter radius on that disk. So the radius from the center here, we could say that that's O, to the outside edge, that's 0.3. And at this particular point, there's a point A that's 60 degrees down from the horizontal, and we have this link AB that's 1.5 meters in length. At this snapshot in time, when we're just looking at a snapshot in time, this angle here with respect to the horizontal is 45 degrees. And it's attached to this piston in this bore at B. So this is really a lot like an engine and connecting rod arrangement. If you look at this point A, that would be like riding around on a crankshaft, right? The crankshaft has some stroke, so we'd look at that 0.3 meters. Then we'd have the connecting rod, A to B, and we would have the piston then constrained in that bore at B. Okay. We're told that this disk is rotating clockwise with 2 radians per second, and alpha for the omega, and alpha is 6 radians per second squared. And what we'd like to find with all this information is the acceleration of B, the acceleration of that piston B, or point B in the bore. Questions before we get started with this? Okay. I'm going to take a coordinate system, x to the right, y up, and z, positive z out of the page. It's important when we start looking at cross products, we're going to be doing some cross products. So this is cross. That's not multiply, that's crossing. The vector cross product, we've got to have a right-hand coordinate system. So we want to make sure that our coordinate system is right-hand. Well, how do we start these problems? Well, we start them almost always the same way. For instance, in this case, I would really like to find the acceleration of B, right? So let's write that down. I could say that the acceleration of B is equal to the acceleration of A. Now, I can't stop there. Obviously, the acceleration of B is not equal to A. It's modified. So I have to add to this the acceleration of B with respect to A. Does that work vectorially? Yeah. The acceleration of B is equal to the acceleration of A plus the acceleration of B with respect to A. So let's expand this a little bit. The acceleration of B then would be equal to the acceleration of A in the normal direction plus the acceleration of A in the tangential direction, right? Because A's moving around that circle. Is it going to have a normal piece and a tangential piece? Absolutely. Then I have to add to it the B with respect to A. Well, B with respect to A is actually going to look a lot like this one right here. It would be B rather than A. So it'll have a normal and tangential piece too, won't it? So I could say that this will be the acceleration of, let's do the tangential first here, B with respect to A in the tangential, plus the acceleration of B with respect to A in the normal. Okay. So I've got those all expanded out. Well, let's see then. So I could say that, let's see, what's this going to look like? The acceleration of B is equal to the acceleration of A in the normal direction. I'll just leave that alone for a little bit. Plus the acceleration of A in the tangential direction. Again, I'm going to leave that alone for a bit. I'd like to concentrate on this acceleration of B with respect to A in the tangential. What's that going to look like? Well, if I assume an alpha and omega for this link, so let me just take that this has some, I'll take this as omega AB and alpha AB. Not to be confused with these values over here. Those are given for the disk or the wheel. But I'm going to assume that this link has some angular velocity, omega AB and alpha AB. You might say, well, how did you assume it was clockwise? I just guessed. Okay? If I'm wrong, I get a negative sign. That's fine. So then when I expand this out, I could say that this would be alpha AB crossed with what? R of B with respect to A. And then that's the tangential piece. And then the normal piece over here is going to be what? Minus omega AB squared times what? R of B with respect to A. Okay. So I've got a lot of filling in to do here, but let me come back and deal with this acceleration in the normal direction, and maybe I will come back and reproduce this wheel down here. That's not very good, but so point A has some, because this is going like this, right? Alpha and omega. This is going to be the acceleration in the normal direction. So there's the acceleration of A in the, not the normal direction, the tangential direction. which if I want just a magnitude, what would that be? Alpha times r, right? Which is going to be equal to, what was alpha? 6 times the radius is 0.3, so I get 1.8. Okay, 1.8. Now I have to figure out the direction in a little bit. And then the normal, there's the acceleration of A in the normal direction. And what's a good way to figure that out? How about our old friend omega squared r? What do we have for omega? We have 2 squared times the radius, 0.3. So what's that turn out to be? 1.2, yeah, 1.2. Okay. And if I go back to this picture, those are acting in this direction that is perpendicular to that and parallel to that, right? Because I'm going to have to break those up. So I can start to put this whole thing together. I can say that the acceleration of B, which way do you think that's going? Well, I certainly don't know the magnitude of the acceleration of B. Let's see if I can sort out its direction. If this wheel is rotating this way, if this link is not to tear apart, wouldn't this be accelerating down? Yeah. So I'm going to take that in the minus J direction. If my assumption is wrong, my magnitude will just come up negative. Okay. So I want to try and wring out everything that I know. Well, I didn't know the magnitude. I think I know the direction, so I'm going to put that there. Now, the acceleration of A in the normal direction. I'm going to have this one here. That's the magnitude, and I will have minus 1.2 times the sine of 30 in the I direction. So I'm just breaking this normal piece up into its I and j components. And then I'll have plus 1.2 times the cosine of 30 in the j direction. So this whole thing is that. Okay.
Why did we say that our acceleration with respect to B, with B with respect to A, the normal direction is negative omega?
This one right here? That comes from right here. Because it's normal acceleration, and normal acceleration is back to the center, the opposite direction of r. I mean, if you don't like that, you could do this. You become a crossing expert. You might say you're kind of cross. Okay. All right. But that's where that negative sign came from.
And then it's the acceleration of A in the normal direction we left off.
Acceleration of A in the normal here? Well, these are just the magnitudes. Yeah, these are the magnitudes. And then I used those magnitudes and I broke this into horizontal and vertical, and then I'm going to have to do the same for that, break it into horizontal and vertical. So are there other questions? Well, let's try that then. So I could say plus, then what am I going to have? Minus 1.8 times the cosine of 30 in the I direction, minus 1.8, because those are both in the negative direction, aren't they? Minus 1.8 times the sine of 30 in the j direction. And all of that is really that one. Okay, so I broke those pieces up. So it's long, it's tedious, it's fraught with places to make mistakes, but it requires really no original thinking. This is the most of our original thinking right there. Okay, so we continue on, don't we? I need to add to this. I need to look at this term here, right? Alpha AB. Do I have an alpha AB? Well, if I use the right-hand rule, alpha AB is going to be what? Minus alpha AB in the k direction. The way that I have assumed this, if you take the fingers of your right hand, put them in the direction there, your thumb is pointing into the paper, which is going to be minus z, isn't it? Minus k. And what am I crossing that with? I'm crossing that with the r vector. So I need to get from A to B. That's the r vector up there, isn't it? So what's that? Well, it's 1.5 times the cosine of 45 in the I plus 1.5 times the sine of 45 in the j. So that's just breaking this link into I and j pieces. Okay, so that's that one done. And then I have one more piece. What's that? I'll have this plus a minus, because I have that minus omega AB. And let's see, I don't know omega AB, so I'll just fess up to that. Omega AB squared times R. Okay, I got that same thing here. I'm just going to multiply it by 1.5 times the cosine of 45 in the I direction plus 1.5 times the sine of 45 in the j direction. That's it. That's all there is to it. Okay. Now, if I go through this, let's count unknowns. I have an unknown here, don't I? That's what I'm looking for. That's a good unknown. I have an unknown here. I'm not interested in that. I don't think I can get it. So hopefully that's the only unknown I get, because I really am looking at a system of two equations, right? When I separate i's and j's, I've got two equations in this thing. No other unknowns, no other unknowns. The real thing that I have to deal with is this. I don't know what that is, but I'm going to have to take a little time out and find what that is. Omega AB. So let's do that. Any questions before we do that? So I'll flip pages here on you. And this will be page number 3. And I'm going to try and find omega AB. Because I've said that is omega AB. Okay. Now if we wanted to, I mean, we could go through and say that the velocity of B is equal to the velocity of A plus the velocity of B with respect to A. I mean, and that would eventually get the omega AB, which would probably be long and not very much fun. What's a probably better way to get omega AB? Instantaneous center, absolutely. So let's use our instantaneous center, and that's why, let's be really clear, we can't shortcut this equation here with the instantaneous center. There is no instantaneous center of zero acceleration, but we can use it to get omega, because this is not an uncommon problem. Oftentimes this comes up, and we have to take it a little aside here, and we have to find the omega. So let me draw the link AB. I'm going to cheat and see what this looks like so I don't run off the paper. So there's the link AB. So that's A. And what do we know at B? I think if our acceleration is going down, it's not a hard step to see that the velocity is probably going down also, isn't it? So let's take our velocity B like this. And what about A? The velocity of A is going to be in the tangential direction. So we would say that it would look something like that, wouldn't it? So then I put a perpendicular here, and I put a perpendicular here, and I have my instantaneous center of zero velocity, right? And I could say that there is the omega AB. Okay. Well, let's see. What do I know? Well, I think I could come up with the velocity of A, right? I could say that this would be equal to the omega, so that's going to be 2 times the radius, which is 0.3, which gives me 0.6 meters per second. Okay, so that's kind of nice. Maybe I'll work out some geometry here. This is what, 1.5 meters. This, I don't know, I'll call it D1. I don't know, do I know this? I'll call it D2. I may not need that one. What angles am I going to have? If I try and find this instantaneous center, it's on this line here, isn't it? If I go to this picture, sometimes it helps to find this thing. There would be the instantaneous center on that picture, wouldn't it? So this angle here is 60, isn't it? Okay. Well, now I'm getting somewhere. Because I could say that D1, what I'm looking for, is to the sine of this angle here. Do I have that angle there? Yeah, 45, isn't it? As this 1.5 is to what? The sine of 60? So I can solve for D1, and D1 turns out to be equal to 1.22 meters. That seems reasonable looking at the entire picture. So now I could say that omega AB, so omega AB is going to be equal to, remember omega in general, omega is equal to velocity divided by r, right? So I take the velocity, 0.6, and I divide that by 1.22 meters, and we come up with 0.4899 radians per second. I've got too many significant figures for a final answer there, but I'll keep quite a bit of those as I substitute that back into the problem to try and avoid round off. You okay with that? Okay. Yes?
This doesn't sound like a silly question, but why is D1 when you find omega AB instead of D2?
Well, if I was interested in the velocity of B here, then I'd be using D2. Okay. If I knew the velocity of B, then I would be using D2 to get the omega. Incidentally, now that I know omega, I could use D2 and I could get the velocity of B, which is again way better than this, right? Okay. But I'm looking at this distance. This is the r distance for this equation. Other questions? So you can't use the instantaneous center directly to get the acceleration, but oftentimes it does come up because you need to find an omega, and I guarantee this is way easier than going through that. Questions with that? So now we go back, and we can say that omega, we need to observe this negative sign, and that's, don't drag the negative sign accidentally into the square and make it go away. It is a negative term. It's outside of the squaring. So we can say that this is going to be 0.48899. So now we go back and we look at this equation, and it has what? Two unknowns. And it's really two equations. So if I continue on with this, so I'll look at that thing. So if I look at all of the j terms, what j terms am I going to have? Well, I'm going to have minus the acceleration of b is equal to 1.2 times the, I guess I got to do some crossing, don't I? Yeah, this could take a while. Okay, that's okay. So, let's start over again here. So I'll do the crossing. So if I cross this thing, I'm going to have minus the acceleration of b in the j direction is equal to minus 1.2 times the sine of 30 in the I plus 1.2 cosine of 30 in the j minus 1.8 cosine 30 in the I minus 1.8 sine 30 in the J. And then I'm going to have alpha crossed with this term here, alpha in the K direction crossed with that in the I. So what's K crossed with I? Should be a positive J, shouldn't it? So I will have minus alpha AB times 1.5 times the cosine of 45, and that's going to be K crossed with I is J. The negative sign stands. Then when I have K crossed with J, I get a negative I, so the negatives go away, and this becomes positive alpha AB times 1.5 times the sine of 45. Alpha AB 1.5 sine of 45, and K crossed with J is a minus I. I took care of the negative because I switched the sign on that. And then here, I actually don't have to do any crossing here, do I? I just say that I have a minus 0.4899 squared. Be careful not to get that negative sign in there. And that's going to be times 1.5 cosine 45 in the I direction. And then we have to also subtract off minus this last term, minus 0.4899 squared times what? 1.5 sine 45 in the J direction. So that was I, that's J. K crossed I is J. K cross J is minus I. Yeah, I think we're good. So once you have those, then you would equate the I's and J's. The I's and the J's. So you'd have two equations and two unknowns. And that would then give you the answer that alpha, which is just a byproduct, we really don't care, that was alpha AB, is equal to 2.28 radians per second squared. And what we really wanted to find out is the acceleration of B is equal to 2.53 meters per second squared. Now that turns out to be a positive number, so what do we think about the direction of that? Well, if it's a positive number, I assumed it as down, so what does that confirm? It is down, yeah. So we could say then that the acceleration of B, our final answer here, is 2.53 meters per second squared down. Okay. So that would be our final answer there. Questions with that? Well, like I said, when we went through this, it's fairly tedious, has lots of pieces, lots of places to make mistakes, but it really doesn't require much creative thinking. The problems are always the same. We'll do one more problem very similar to this. Again, same process, just to get a little more practice when we get together next time. And then after that, we're going to move on to kinetics of rigid bodies and start talking about mass, moment of inertia, and things like that. So that's where we'll go from here. Take care.